Well, first of all, I want to thank everyone for joining. There'll be more that are coming online now. So let me first make a quick introduction. Uh, Today's webinar, Mastering Fatigue Testing with Force Measurement, is going to be presented by Brian Peters, who is our Vice President of Global Worldwide Sales, and also a very experienced engineer who's been implementing solutions for decade plus, a couple decades in there somewhere at the interface. And then we have Peter Baldwin, who is also an applications engineer with Interface, and he will be presenting as well. Today's webinar again features fatigue testing. We have a full agenda today. As you can see here, we'll be covering fatigue testing basics, and then they're going to drill into some design and material characterizations real quick. We'll then talk about different types of sensors that are used for fatigue testing, the high frequency testing best practices. We'll get into some testing configurations and considerations along with data interpretation. And then we'll dive into some engineering tips, get a little technical with instrumentation challenges and solutions, finish up with a couple of use cases, and then some of the top frequently asked questions. There's a lot to cover in this quick hour, so we want to get into as much material as possible. So with that, I'm going to hand it over to Brian and Peter.
Very good. Thanks, Jamie. Go ahead, Peter. Let's kick things off.
All right, excellent. Next, please. All right, so primary question we need to start with is why are we doing this? Well, we need to validate the process, the material, our operation. We're looking to validate the life expectancy of the product. We want to be able to have fatigue data for that validation and for any liability purposes, And we want to be able to demonstrate the safety of a particular structure that may be susceptible to widespread fatigue damage, FEA, model validation, confirm or negate any expectations for crack initiation and growth pattern, identify critical locations and acceptable assembly methods, and then validate the proposed maintenance schedule. All of that is kind of incorporated in what we're going to cover today. Right? So as part of those basics, implementation of load cells in a data logging system are a necessity where materials, parts, and assemblies are fatigue tested for verification of life cycle all the way to destruction. You want to be able to have an accurate record of those forces over that testing period to analyze the stresses which occurred prior to and during the ultimate failure. And keep in mind, predicting exactly when that failure occurs or defining which part of that assembly will be the weakest link can often be very difficult. Okay. So as part of those basics, we need to understand the quality of our test equipment. When designing a test protocol, you have to give serious thought to the possibility that some of the test parameters might change along the way, or that there might be different aspects of the test as part of the test cycle. So what might change? The test frequencies themselves, the force levels on a given test, location or angle of the force application, accommodating the test setup with variations or component improvements, and how to respond at failure. So using the equipment that can accommodate some range of alteration without a major redesign of fixtures would be quite helpful to the project. Okay. And so as we progress, there are typically two types of fatigue failure, two important aspects. There's a high cycle and a low cycle fatigue. High cycle fatigue refers to relatively low stress loads acting on the mechanical component that leads to fatigue failure over millions of load cycles. Whereas the low cycle fatigue uses higher stress loads that would lead to failure using fewer number of cycles. Okay. There's three stages of structural fatigue failure. Repeated cycling builds up local plastic deformation and a microscopic crack is then initiated. As the test continues, that crack propagates and a larger section then becomes weakened. And then the stress concentration as the test further continues in the selection of The cracking increases rapidly and continued cycling enlarges the crack until there's a sudden fracture.
Okay, thanks, Peter. Next section. So we've talked a little bit about how, the basics of fatigue testing, how it can be difficult to characterize the exact time and mode of failure. So go ahead, next slide, please, Jamie. Typically what you want to be utilizing, or it's kind of common done, rather than just start a test of a number of cycles, known cycles, and break the part or get the data, we'll use force feedback, obviously, as part of that. So there's different aspects there you want to keep in mind. We already said, fatigue life prediction can be pretty difficult. Sure, you can calculate it. The calculations are usually going to assume pretty linear behavior from a material standpoint. However, as things start to get exposed to adequate cycles, especially near their limits, you start to introduce nonlinearity within the material. So as Peter alluded, you start to develop some damage, starts to maybe develop a small crack, as was mentioned, which propagates further. But again, there's nonlinearity aspects. So testing is what's necessary, and load cells are the proper way to approach that. So next slide. So there's a couple things you want to think about in your test setup, and this includes the load string, and it's also going to include the load cell. But the materials are pretty important. Anytime you're doing really high cycle counts, it's going to come down to, again, we're trying to strain material somewhere where you're straining everything in that assembly. So a good rule of thumb is to look at these primary characteristics and make sure they're well suited. So composition, alloy mix are a good way to increase strength, but really want to make sure you're working off of good, pure material. And that works down to the microstructure level. So consistent grains, low impurities, as mentioned. Ductility is a good characteristic, not always critical that you have a highly ductile part, but it certainly lends itself well for extended deformation or accommodating deformation and not just cracking right away. And of course, more ductile materials should have a higher fatigue life. Hardness is a good property as well. We don't want to allow it to start to deform. That'll certainly most likely cause some areas for stress concentration and crack propagation to then initiate from there. Surface conditions, pay attention to that. We want to have smooth surfaces on all of our load fixtures, everything in the assembly. Again, all starts with cracks, and also pay attention to any residual stresses depending on how that material was tempered or finished. So next slide. All right, speaking from a load cell standpoint, load cells are built from several different materials. Interface load common materials are going to be aluminum, steel, and stainless steel listed below. But it's usually going to be a compromise, right? So a load cell is going to be designed in terms of how do we provide the highest signal, the best measurement, while still accommodating whatever the desired force levels may be. So it's a balance. We can certainly make a load cell that provides a great signal and may not last very long, or we can provide a very low load cell signal that will absolutely tolerate nearly any force you can throw at it, right? But it all comes down to managing stress targets, specifically relative to the material's SN curves. So we'll do a little bit more on that, but engineers target, the beam thickness. Beams are where we apply the strain gauges to ensure, again, that the bridge is going to give the desired output. Some of our load cells are 4 millivolt per volt, for example, as standard output. Most of our fatigue are going to be at a lower level than that, around 2 millivolt per volt. Still, that's often what many of our competitors offer as a standard output. So everything's relative, but everything is a compromise. So, but for these common materials, aluminum, we use 2024 aluminum, 4340 steel, very particular in terms of where we get the material, how it's processed. And then 17.4 stainless steel as well for some applications. 17.4 is good for high hermetic requirements. However, it's not always the best choice from our perspective for very high cycle, just due to the fact there's welding and some other aspects involved in there. So you won't see too many stainless steel fatigue rated options from Interface. Not saying that we can't use them though. We'll get into that later. So next slide. So SN curve, what is that? Well, it's basically a graphical representation, and I'll show it on the next slide here, that it's pretty well known from a material standpoint, but it is a way to describe a limit, if you will, in terms of the applied stress and the number of cycles. So that's the S and the N for an SN curve. Some materials certainly have a level that if you stay below that threshold, will have an infinite life. Not all of them do, though, however. So we want to make sure that, again, we're going to handle the load cell part, but everything else in your load string or your test article, you need to be thinking about that SN curve. You don't want to have a premature failure well ahead of what you expected. So again, pretty basics of design, but something that is overlooked maybe on other components, including fasteners. So next slide. So here is an example of two common material SN curves that Interface uses for fatigue-rated load cells. So on the left is an SN curve representative of steel, stainless steel. And interestingly, if you zoom in a little bit, hopefully you can see, you'll see where we target stress levels, operating stress levels at full capacity, of course, for our non-fatigue rated models. So these are all low profile families, but 1100, 1200, 1300, they'll operate in the 55 KSI type range. Our fatigue rated load cells, we target them to be operating much lower, around 25 to 30, to ensure, again, that it's well below the endurance limit, okay? So that endurance limit there on the right side of the left graph, as long as stress levels stay below that, you have essentially infinite life in the material, right? So that's the goal. Want to make sure to stay below it. Now, the 1000 series is pretty far below that endurance limit. Why? Well, we'll get into that in a little bit. But that's just an example for steel, stainless steel. And then on the right, we have aluminum. Now, aluminum SN curve, that red line, looks a little different. As most of you on here probably know, aluminum doesn't necessarily have a fatigue life. So that means that for our lower capacity LPs that are aluminum, we're going to design them at an even lower strain level. Now, of course, our strain gauges are sized and designed and selected from a material standpoint to make sure that we get good electrical signal, electrical output from the sensor. But it just gives you a good idea of where the aluminum stress levels are operated at relative to steel, and Interface's approach from an SN curve to ensure that the load cell is going to have a very long, safe, healthy life. Next slide. All right, fatigue testing sensors. So let's start talking a little bit about specific sensors. I'll keep going on this one, Jamie. Interface, since 1968, has been dabbling and offering, I shouldn't say dabble, offering very high precision fatigue rated solutions. So some of our earliest load cells were actually fatigue rated, given the primary markets we were serving at the time, aerospace testing, for example. But an Interface fatigue rated load cell is guaranteed for a minimum of 100 million fully reversed cycles. What does that mean? Fully reversed. So that means if it's a universal load cell, good for tension and compression, you're going to the full scale value immediately to the other full scale value. So that's a pretty tough loading condition. Most tests aren't going to be quite that severe, but we guarantee fatigue rated Interface load cell will meet that requirement. In fact, in our many years of selling fatigue rated load cells, we haven't had one come back due to a fatigue failure specifically. So again, part of that's due to our conservative approach, but there's also other reasons why we have that conservative approach relative to the SN curve. But you can have confidence that Interface fatigue rated units will certainly work for your application. Again, and say, well, we have a fatigue test. Well, okay, well, how many cycles is it? It's a couple thousand cycles. No, you're going to be fine with a standard product. We'll talk more on that too. So again, if you're going to have the most demanding, very high cycle, fatigue is where you want to go. 100 million fully reversed cycles, you'll be hearing that a few more times here today. Next slide. So as we talked about, just a quick summary again, Interface fatigue rated are going to be operating on those lower levels to ensure that you're going to have a high life. Typically, the strain levels and corresponding output levels will be about half of what are standard. So again, instead of 4, it might be a 2 millivolt per volt output. Next slide. We make sure with our sensors from a fatigue standpoint that we minimize any high stress points. We talked about that earlier from a material aspect, surface finishes are smooth. Our fatigue rated load cells have additional extraneous load rejection, so much higher ability to tolerate off-axis loads. We'll talk more about why that's important. But as we said, 100 million fully reversed full capacity loading cycles guaranteed from all of our fatigue-rated load cells. Next slide. I will touch on that Interface's sensors, for the most part, rely on foil-based strain gauge solutions. There are other options when it comes to force measurement, specifically around dynamic loadings. Often piezoelectric load cells are used for, I would say, impact type loading. But as we're going to explain here, foil-based strain gauges are still very well suited for very dynamic applications as long as you understand the limits and how to work with them. Differences between the two different strain gauge types. Well, foil-based strain gauges, that's going to give you the best performance, best accuracies, especially from a thermal standpoint, and especially given our proprietary load cells are thermally matched and we don't need to add mod resistors and everything else to our circuit. So interface load cells are inherently going to perform better than anything else out there from a temperature stability standpoint. 4 millivolt per volt may be relatively lower, but again, ours are a little higher than most foil-based, and maybe a little bit lower dynamic range, which we'll get into. But piezoelectric, another option, good for impact style testing, less accurate, much less stable, and they're inherently just designed to only measure a change in force. So they're not going to be good, certainly, for any sort of static or long-term type loading. High signal, which is a positive, but again, very high sensitivity to temperature. But they're going to be on a very stiff element, good for natural frequency, which we'll talk about, but they do require very specific and much more complicated instrumentation. So just for reference, again, we're going to be talking mostly on foil strain gauge solutions today. There are other options. And again, if there's any question about your application, of course, we have application engineers standing by to point you in the best solution direction. But next slide. Okay, so our most popular, and I'd say probably one of our original 1000 is it fatigue rated load cells. Sorry, I got sidetracked there. Oh, can you guys hear me okay? Peter, Jamie, is my mic coming across okay?
Yes.
Okay, good. All right, there was something about speakers. So our most popular fatigue rated solution is going to be our 1000 series. This is based on our very popular and very reliable low profile family. These capacities start at 250 pounds, go up to million-pound force. Very versatile, very rugged, very high rejection to side loads, eccentric loads, which are very critical for fatigue. We'll mention that in a minute here. Very high accuracy, and of course, spaces are offered and always encouraged. Please, if you buy a low profile, get it with a base. But these do offer very high safe overload as well. So instead of the typical 150%, you're going to get 300%. And as mentioned earlier, very low off-axis sensitivity on the order of, well, actually guaranteed to be less than 0.1% per inch and 100 million full reverse cycles. And of course, many different options, whether it's multiple bridges, different connector types, connector protectors, TEDs, you name it, we can offer it on these. Next slide. We offer other pancake style solutions, low profile solutions that are also fatigue rated. Again, fatigue rated, 100 million fully reverse cycles. So two more to highlight here are going to be our 1208 series and our 1700 series. Both of these are, I would say, more popular in the European market, but they're still great choices, partly due to the ease of assembly. So the 1208 looks very similar to the 1000 series you saw earlier. However, it incorporates a multiple bolt pattern center flange. It's recessed on the bottom, so you can actually put cap screws up through that and attach specifically to actuators. There's other actuator types out there that have specific bolt patterns, or if you're in a really high capacity, it's a lot more convenient to not have to deal with a single large thread, which a big LP with a base on it becomes not the lightest sensor, and from an assembly standpoint, these are a great option. But they're also fatigue rated. Not a lot of people know that. Wide range of capacities, good safe overload, and also less sensitive to off-axis loads than, say, a standard 1200 series, and again, 100 million fully reverse cycles. 1700 is a similar model, much more unique and specific flange pattern to accommodate very industry standard bolt patterns on the actuators. So again, in Europe and other places, actuators come with different mating surfaces, and we have solutions to mate up with them. And again, because they're going to be tied to actuators, most of the time you're doing cycle testing, right? So it makes sense that these are fatigue rated. Next slide. 1500 series, this is going to be a great fatigue rated and moment insensitive option for lower capacities. It starts at 25 pounds, goes to 300 pounds. Similar axial safe overload as some of our other products, 150%, but it is obviously fatigue rated with 100 million fully reverse cycles. And of course, we can do standard or typical, I should say, options on this like we do with many of our other sensors. Next slide. Miniature S types. We offer a lot of different flavors of S types. We do offer a few that are specifically rated for fatigue use. So the SSMF, Super SC, and I think an MBI, which isn't on here because it's not an S type, but that's a cantilever beam fatigue rated option. So we do have many options. If you're stuck with a form factor or you need a certain capacity and you don't see a fatigue option, that's the best time to call and reach out to us. The reality, if you go to the next page here, Jamie, the reality is a lot of sensors can be used in fatigue. Don't necessarily be afraid to use something in a fatigue test, but it's really important that you understand the loads it's going to see, and you discuss with one of our application engineers to make sure it's operating at a lower limit, and you've also taken into account other aspects to make sure that it's going to be adequate for your use. So we make quite a few other flavors, but again, maybe you don't need 100 million fully reversed cycles. Most of our standard products are going to be good for at least 1 million, if not more, again, fully reversed. So 1 million fully reversed, which would translate to millions of cycles if used maybe only in compression or only in tension or not going to full scale every time. So again, just for reference, non-fatigue rated target there would be about 1 million without any concern. If you need to do a couple million with a non-fatigue rated load cell, talk with us and we'll get the capacity size accordingly. So I keep saying that. What does that mean? Go to the next slide, please, Jamie. So selecting the capacity of load cell is one of the most important things. It's one of the first things you start with. It's really important to understand a couple different values when it relates to that. So we'll have a rated capacity, right, or a full capacity for a load cell. That'll be the stated capacity. And then above that, we're going to have what's called a safe overload. I've referred to that a few times earlier. Usually it's about 150% for a typical sensor, but make sure you take note of it. It does vary and certainly varies by manufacturer. And then above that 150%, you start to go into actual damage. Okay, now what is that? Now let me back up. So safe overload range, what does that mean? Well, it's a range that you can go to, and sporadically, if you need to go to that value above the capacity, you certainly can. As long as it's done not too often, sporadically, you're not going to have any issues with the load cell. Now, if you're continually working up to that safe overload, yeah, you might start to see a little bit of damage. Now, how's the damage going to start to show? Typically, it's going to be a zero shift. So the zero value, bridge value is going to start to move a little bit over time. And then, of course, you get all the way to the ultimate overload. And that's going to be around 300% for most sensors. Of course, you'll have mechanical damage and separation. Now, the safe overload, it's okay to get into that range if necessary. However, we can't guarantee performance, right? We actually exercise every load cell before calibration or as part of calibration, right when we first hook it up, over capacity. We all actually exercise it usually to about 140% of 130 to 140% of the capacity, and ensure that everything is settled in the load string, everything's properly tightened, and we have the thread preload where we'd like it, and then we start our calibration. So again, getting into that safe overload, not recommended, especially if you don't have certainty of axial load isolation, which we'll talk about as well. But you can get in there if you need to. Now, what does this have to do with using non-fatigue rated load cells? Well, you can understand that if you're operating at half of a given capacity regularly at high cycles, you're likely going to be okay, right? Even a non-fatigue rated interface load cell, good for 1 million, maybe 2, fully reversed at rated capacity. But let's say you need to come up with or use a form factor or a particular solution that isn't fatigue rated. Well, if you size the capacity to where your testing is going to stay below that maybe half range, you'll likely be fine for tens of millions of cycles. So it's really just a matter of understanding the capacity and the actual test loads. Hopefully that makes sense. All right, next slide. Now, when you are using load cells in fatigue testing, more so than ever, how you attach to them is super important. Even from a calibration standpoint, optimal performance standpoint, you want to make sure you follow all of our recommended installation instructions. We have those for the different models available. But when you're doing high cycle count, it's even more critical. So want to make sure that everything in your load string has good tight connections in terms of the thread engagement. We always recommend preloading. So the published torque values for our low profiles will adequately preload the threads in the load cell. Above a certain capacity, we recommend customers just preload to above test range or even above capacity if you can, and then finger tighten the jam nut, relax it. Now you've ensured that all those threads in the load cell are going to be at a higher strain that you're going to see oscillate through your test. Now, fatigue testing, you want to make sure that you do a good job of isolating to ideally whatever the preferred load or axis is of the load cell. So if it's an axial load cell, that you've done a good job to isolate any side loads or bending loads. We'll talk some more on that. But as you can imagine, high cycles will start to compound that if you don't have things perfectly isolated. Now, always recommend using sphericals or rod end bearings where you can, or even just clevises maybe if necessary, just to ensure that you're minimizing any bending or side loads to go through the load string, through the load cell. And now the other aspect too, since you're doing cycling generally with fatigue testing, a perfectly acceptable approach for a compression only test would be as what's depicted on the left there. That isn't necessarily ideal for fatigue testing because you don't have a permanent mechanical attachment there between the, in this case, the representative flat surface loading the compression button on the compression only load cell. Anytime you're doing cycle testing, if you're, depending on how much you're relaxing that force and or how quickly you're cycling, you have the potential risk to develop a gap. And if you develop a gap between your loading surface and your load cell, the subsequent closure of that gap can result in very high shock loads to the sensor. So we always recommend, even if you're doing compression only, still a good idea to get a universal load cell just because you have the ability to actually thread in and engage on the load cell in a permanent manner. Don't want to have any sort of gaps or separation in your load string that can develop very high shock loads very quickly. All right, next slide. All right, so we talked about importance of good tight threads. We talked about load isolation. Also need to pay attention to the quality of the threads. We specifically call out Class 3A attachment hardware anytime you're threading into one of our low profile load cells. Also for fatigue testing, you want to look at the quality and the strength of the fasteners that you're using. If you're using a non-fatigue rated load cell, for example, you may have attachment hardware sized in a manner that now becomes one of your weaker links. So you might need to plan to stop the test after X number of cycles, change out some of the mounting hardware, and then resume. So don't lose sight of everything in the string. But not only is having good thread engagement, like Class 3A, for example, on the low profile is important from a reliability standpoint, it's also critical from a performance standpoint. So if you don't follow what we put in the recommended installation guide for a low profile, for example, you can have up to 15 times impact to your test data. So in other words, trying to hit our 0.04% SEB value that we state, if you're not using good Class 3A threads, you're not following the preload or recommended torque values, you're probably not going to get there. You're going to have a little bit of more error on the linearity hysteresis side than you'd hope for. Next slide. All right, other aspect in mounting, pay attention to the live end versus dead end of a sensor. Those of you that have been in some of our webinars know that we've touched on this quite a bit. Essentially, the best way to think of it is whichever end of the load cell has the cable coming out of it, you want to direct the force input on the other end. And you want to retain the cable on what is then the dead end. So easiest way to depict this is the S cell on the right there. So behind our label, that little blue label there is where the gauges are. There's actually a little round cavity in there. We've got gauges on the top and bottom of it. And so you can imagine that if that's where the force sensing is happening, right? If you were to strain relief the cable below it, it's not impacting the measurement. Now, if you were to pull that cable up and strain relief something on the top side of the string, well, now you have the cable influence impacting through a parasitic load path through the area of the bridge in terms of what should only be seen, the axial load that's coming through the end of the load cell, right? So always want to make sure you strain relief the cable on the dead end of the bridge, the dead side. Again, look for where the connector comes out or the cable comes out. That's going to be your clue there. And then also just for fatigue testing, best practice, if you've got a long stroke or a long test translation, please make sure you've adequately strain relief the cable. You don't want to have a signal go down and lose that measurement 80% through the test just because a cable fatigued, right? Okay, next slide. High frequency, I think that's back to you, Peter. Go ahead.
It is. Thank you. All right, very good. Next slide, please. All right, so now that we've discussed the load cell, there's other aspects to it as well, so we want to talk about that. There are factors that make fatigue life difficult to characterize in any structure. Controlled tests on the simplest configurations of your test specimens result in a wide scatter band of results, so analysis is even more complex when you have complex structures typical of a load cell. So theoretical analysis can produce an approximation. However, it can be useful in estimating the margin of safety at a particular load cell when a load cell design is operating. All right, next slide, please. All right, the component subject to failure. So as still talking about the load cell, the two metal components in a load cell must be considered in your fatigue analysis. There's the flexure, which is your spring element, and the strain gauge, which is your sensor. So the flexure bears the load. Therefore, any failure of the flexure is going to be structural, and with the gauges correspondingly glued, calibrated to the internals of the load cell, the function is producing an electrical measurement with minute deflections in that metal. Failure of the strain gauges, however, on the other hand, are not typical, typically not structural. Failure is noted by a shift in resistance or the gauge factor. So the relative propensity to first encounter flexure or strain gauge fatigue failure depends upon the design of that transducer. All right. So again, we're still talking about the load cell. Inside our data sheets, this happens to be the 1200, but it represents the natural frequency of the several different capacities. And so whatever your test function is in terms of your test plan development, you need to be operating at something slower than that natural frequency. You're not going to capture anything faster than that. The metal just can't, it's just not going to translate electrically through the circuit. Okay, so whatever you do.
Yeah, it's a good way to think of the load cell. It's a spring, right? It's a stiff spring, and you start operating above the natural frequency, and that spring's going to be underdamped significantly. So,
very good. Thank you. All right, next slide.
Oh, just real quick. Just wanted to touch on the fact that that's the specification natural frequency of our load cells, right? So to give you some idea of the mechanical stiffness, the mechanical characteristics there. But when you're actually looking at your tests, you have to look at the entire load string, right? You got to look at everything else that's attached to it, attached to that load cell, the masses involved, and then of course look at how that's going to arrive at a system level resonance frequency. So go ahead.
All right, thank you. All right, so you have your resonance frequency of the system. That's going to vary with the applied load. Mechanical response will always be the primary limit. Your gauge and electrical signal response are negligible consideration. So your best practice for minimal underdamping is to target 10% of that load cell's natural frequency. Typically, we see load systems arriving somewhere around 60 hertz after factoring in that loading.
Yeah, so if you're operating under 10% of natural frequency, you really have nothing to be concerned of. If you're going to be over that, we certainly could take a look at it and work through some of that. As you start to obviously get closer and closer to natural frequency, of course, your chance of error or phase alignment challenges will increase. So, all
right, very good. So part of that data collection is going to be your DAC. There might also be an amplifier in there. We'll get to that in just a minute. But looking at the diagram on the right, there was something that happened. Something changed that caused that particular waveform to happen. If what we're looking to do is to capture that, how fast do I have to run that DAC to be able to accommodate that? Well, as you look at a sinusoid on the left, if I just take two samples, it just so happens in the diagram to show peak and valley, but the chances of actually capturing that peak and valley when we're only running at twice the operating speed of the load cell is very minute. Okay, so what if we choose 4 times on the DAC of whatever the operating frequency is of the load cell? Well, again, it doesn't really equate to replicating the waveform. That could be a sine wave, that could be a sawtooth, but there's not enough data points there to actually capture what happened on that particular waveform. So the rule of thumb, as you can see that far right sinusoid, in that it shows 8, but the rule of thumb is actually 10 times faster than whatever you're operating that load cell at. that would allow you to capture these type of transitions and changes in the output. So how might we do that? Well, one of the things that we have is a BX8. This comes in a couple different formats. This just happens to be one of them, but all three offer the same type of digitizing. This is 48,000 samples per second. It's a 24-bit DAC. If you can look on the right-hand side, the input filter goes up to 11K. The output filter goes up to 15K. So by and large, that's going to accommodate any type of testing that we're going to be accommodating on our setup.
All right, thanks, Peter. All right, so we talked earlier that the strain gauge itself has pretty negligible influence, even in high cycle. The bridge response is going to be nearly instantaneous, and you're almost always going to be limited by the mechanical aspects of your load string or your entire test setup. So we talked a little bit about the natural frequency response, the stiffness of the load cell as being something you want to look at, make sure it's sized appropriately. But just general understanding of what's happening and what's occurring from a mechanical standpoint is typically more important, especially in many years of helping customers do testing. This is usually what comes up as something that was not expected. So mechanical limits. If you don't have things sized properly or you haven't considered all mechanical aspects, it's going to impact the accuracy, validity, and scope, and of course, even if you complete the test, right? So it's going to be partly related, of course, to the load cell. Then you got to look at the overall stiffness of your setup, whether that be a particular material test frame, or if you're building something with a T-slot floor or something, have you properly sized all of the load-bearing elements? If you're doing coupon testing, the grip and fixture design, if you're using a commercially provided material test, of course, they have a whole catalog of different grip and fixture options there. Also environmental. Do you have a consistent testing conditions, for example? Do you have some thermal concerns, which we'll get to, that may impact it? Then, of course, the actual specimen. You may have some aspects of the design or geometry that maybe FEA didn't quite alert you to, or maybe that's going to be a concern. So you may need to then decide, given you've got a hot area here that you have to be careful of, maybe that's going to dictate different arrangement of actuators or force introduction, right? And then there's the dynamic aspects. So, frequency, you start going really high speed, what starts to happen there? Both again from your measurement, ability to take the measurement, but then also inertial or mechanical, or if you're testing to failure, what are the dynamic results of a failure? What's going to then happen to the rest of your setup? Are you pretty much going to have to write off the load cell, for example, or can you size it in a way that even the dynamic load, inertial load following separation there won't damage the bridge of the load cell, right? So these are all things to think about. All right, next slide. So we spent some time talking about sizing the load cell from a capacity standpoint, and if everything's axial, that's pretty straightforward, right? We saw the simple little graphical representation. You've got your operating range, you've got safe load 150% or 300%. And then above there, you start to get some zero shift and bridge damage. Okay, well, things get a lot more complicated if you've got any side or bending or off axis. And 8 times out of 10, there's more in a test setup than customers expect. So extraneous loads, really good thing to understand. And it's partly why we always recommend the 1000 series as the preferred fatigue test solution. Why? Well, because we know a lot about them. Next slide. So we've been building low profiles for a long time, and some of you that have been using them for a while know that this is one thing we do, but we actually moment compensate every single low profile that we make. So moment compensation is a method of bolting the load cell down to a fixture, hang a weight off, usually about a foot off, pretty high weight. We swing that weight around and we see how the load cell signal changes. Okay, now that's it's going to give you confidence that if you throw it into a basic application, the load cell is going to do a good job to not be influenced by any off-axis loads and give you good, accurate measurements from the axial component. That's great. But it also allows us to, because we do this, because we have specs around this, we know exactly how the load cells can take other extraneous loads and how that's going to, A, impact either the accuracy of the signal, or B, how it's going to impact the life of the sensor. So this table here on the left is a snippet from what we call our composite loading worksheet, which presents an equation here that allows you to look at a calculated theoretical strain sum value, it's kind of unitless, as a function of your input loads. Okay. So let's say we have a test and we know what the axial is, great. And we know we're going to have some side or maybe some bending, and we've got an actuator we can't fully neutralize its weight effect. We can help you work through how much life you're going to get out of the sensor. So the next slide, we've got a few examples here. This is looking at a 1010 ACK 250 model, so pretty low capacity, fatigue rated. And we've got a couple different loading conditions here. We kept the little table on the right there so you can see for reference, but we got 3 different loading conditions on the left. One is 220 pounds with 10 pounds force side load. End up with a calculated S-sum value of 30. So that is right there at the fatigue rated stress strain value. And this is still good for 100 million fully reversed cycles, even though we've got a little bit of a side load. Now, you notice it's not full scale axial, right? That gives us a little bit of overrange to be able to accommodate some off-axis loads. Now, a couple other examples. Let's say we go to 250 pounds full scale capacity, but we have a little bit of side load. We'll see now we've bumped above the 30 value, and now we're looking at, yeah, it's still going to be fine for, millions of cycles, but it's not going to be probably good for 100 million fully reversed cycles anymore, right? Now, let's say we have 220 pound axial, but we've got 100 pound force inch moment on it. What does that mean? Well, now we're looking at an S-sum of about 62.4, which it may not even make a million cycles anymore. Okay, so like I said, if you've got a test setup or you're concerned about ability to isolate, we can certainly walk you through it. This calculation is a lot more difficult to make on other form factors, things that aren't perfectly symmetric, of course. But the low profiles, the 1000 series, we know inside and out, and we can application engineer can walk you through your test setup. Next slide. So I mentioned it before. Customers often think that they're imparting maybe only an axial force, and they're wondering why they have to replace sensors after a few thousand cycles or a couple months of testing, and think it's the sensor. Okay, well, maybe they replace it with the same capacity thing. Maybe something wrong with the sensor. They replace it, put the same capacity in. Next thing you know, they've got another failure. Okay, well, let's go up in capacity. Maybe they go up another 50% in capacity. They run. Maybe the test runs longer. You get another failure. Okay, well, what's going on here, right? Well, we've often recommended at that point our 5200 series, which is a great drop-in for our low profile. That gives you the insight of MX and MY moment data. So instead of just having the axial, like a 1200 series, now you have MX, MY moment data. And usually what customers are going to find is it wasn't a purely axial test. And guess what? There was a side load element to it. And that's why, if you think back to that S-sum equation we were looking at earlier, they were actually seeing more load than they thought and ended up breaking load cells. So again, we really, really recommend this unit. I don't think we sell as much as we should, just because it's always great to get more data. And it's really helpful for you to be able to confirm, are you seeing what you want? And okay, maybe you don't break the load cell. Well, all that test data then maybe has a little bit of moment error in there. Yes, if you're using an interface load profile, you can calculate worst case error. Thankfully, if you're using another load cell, probably not. But you have the error influence. And then, you're still just not getting that additional data. So, all right, next slide. So uncertainty. So you're going to have some level of uncertainty in the test. With any test setup, you've got usually it's going to come down to your load cell performance factors and things of that nature. But you can certainly have in a fatigue test scenario additional aspects. Are you getting any material availability, variability, or any change in mechanical stiffness of the rest of your fixturing? Oftentimes, when customers come to us with calibration challenges, let's say they may not be getting the same calibration performance that we did, we always look at fixturing. Say, okay, give us a picture of your test setup, how you're connecting to it. So again, just keep that in mind with the rest of your test setup. You can have the best sensor spec, but if you haven't taken the rest of the assembly into account, you may not be getting the data that you're thinking you are. Oh, and just in reference to that previous example, we talked about the error influence that can be developing, but you also aren't necessarily testing your product or whatever it might be to the same input forces that you thought you were, right? Usually fatigue testing is a culmination of FEA or other analysis, modal analysis to say, okay, now let's go validate our models that we've developed. Well, again, if you were seeing side loads or introducing bending into your test article that you didn't think you were, it kind of throws a lot of that out the window, right? Because it wasn't in your force case scenario. So anyways, But back to this, as far as things that impact uncertainty, test setup, execution, how well do you have things isolated, the fatigue behavior itself. Maybe you're starting to get into if it's really high cycle, high frequency, you've got some phase lag and or under damping happening to the system. And then again, how are you analyzing the data? Are you capturing it quick enough? Are you capturing everything you think you are? Again, you may look at the data and think, okay, it says this. Well, if you've missed some peaks or you missed some valleys, that can change things quite a bit. And then how stable is your test environment? Is temperature changing? Is humidity changing? Any of those factors you want to keep in mind, again, because fatigue testing is often done over a much longer duration. Next slide.
Back to me, Jamie. All right.
Actually, I'll cover this, Peter.
All right, sir.
All right, so testing configurations, data interpretation. So we'll go through this kind of quick, but when you're setting up a fatigue test, there's different ways that you can apply loads to a test article, right? Very simple, very easy axial, specifically vertical, right? That's the easiest and cleanest test setup. Cantilever bending, also very popular for fatigue testing. Say you're wanting to test something with that's under a side load, you need to fixate that. The good news there is you're likely going to be using an axial force introduction, which is good. Torsional testing is popular. This can either be done through an actual reaction torque sensor inline, or you can maybe do the torsional loading through a moment arm, right? Obviously, going back to an axial force input is going to be the easiest, cleanest, best way to isolate loads. It simplifies the sensor. But again, sometimes you might want to get that actual inline torsional force just to eliminate any joints or anything else impacting that. Next slide. Great if you only have a single input force. Real world parts usually see more than that, especially a lot of our aerospace customers are testing components that are seeing forces coming in from all different directions. Again, ideally, we always recommend isolation of those input loads, having actuators aligned with single sensors. Best way to do it. Just pay attention. Okay, as you start to push, how does that force maybe translate to another sensor, right? And how does it correlate through the test article? We've actually had customers moving towards instead of just anchoring something down and putting input forces into it, actually getting the reaction loads via multi-axis sensors underneath that. So, and that kind of leads to the next test setup here, which is multi-axial loading. So maybe you need to you have a single boundary condition where you're anchoring the test article, but you're actually imparting multiple forces through it, and now your reactive or your anchor force now is seeing multiple axis loading at the same time. So we do offer a wide range of multi-axis sensors, so we certainly can do it. Just have to pay attention to a couple things there. But multi-axis, sometimes it's the only option for fatigue testing. We typically recommend, again, isolating if you can. But if you need to, we have multi-axis solutions there. Next slide. High frequency fatigue. So we talked about this. There's the mechanical, natural frequency, resonant frequency considerations you want to take into account. Also, make sure you're up on the DATAAC sample rate. High frequency, very high speed testing is a great way to consolidate development time or to shorten it. Just keep in mind, it's obviously going to introduce some other challenges. Thermal and or environmental fatigue testing. So it's real common, especially with some of the material test frames, to have environmental chambers around your test article. Makes sense. You may need to test at a high temperature, may need to test in a corrosive environment. That's fine. Just do everything you can to get the sensors outside of that, right? And keep them isolated. Now, even if the load cell is outside of the thermal chamber, what kind of temperature are you seeing propagate through the load string, right? That's something else to keep in mind. So the better you can thermally isolate the sensor, the more accurate data you're going to get. However, there's certainly ways you can characterize that data. And again, application engineers are standing by to talk through that. So if you have to seal, if let's say you're trying to do something in a pressurized environment, that's great. You have the sensor outside of it. Don't forget the effect of the seals or any sort of parasitic load path that might be there as a result of that. So in general, the sensor selection is critical. We talked a lot about choosing the right capacity. Also, just make sure you chose the right type of sensor. So if you are having a scenario where you're going to have, let's say, primarily a torsional load, but you're going to see a side load, it's best to probably start with a properly configured torsional sensor. Again, probably not a fatigue rated, but we can help select the best option that's going to reject that. If you're doing multi-axis, kind of jumping over there, start with the correct one to begin with. So if you're doing high axial, low shear, or low bending, then maybe start with what used to be a 1200 series, for example. If you're starting with, you need more accurate measurement or a higher torque measurement, start with one of our 5400 series sensors that then has the axial bridge added to it, if you need to pick up the axial force, for example. So jumping back though to sensor selection, we talked about capacity, we talked about, make sure the right type, location, where do you have it placed, how are you securing the cable, any parasitic load paths in that system. Load isolation, next most important, as we showed there, it can dramatically reduce the life of the load cell. If you have it's real common in, fuselage testing, for example, you've got big, long runs, maybe for your horizontal actuators that are maybe putting relatively small loads in there, of course. Then you want to do everything you can to neutralize the mass effect of those actuators, so it doesn't manifest as a pretty significant static side load if you can. Again, ideally, the sensors just want to see the load they're designed to measure and minimize any other loads from popping up in there. And then sensor alignment, of course, how are you mounting it? Is there better ways to mount it to minimize side loading? The multi-axis, if you do have to go with a multi-axis sensor, and you are looking at fatigue, again, we can help size the capacity that will tolerate not only the cycle count, but also accommodate all of your desired or necessary loading conditions. There's a couple different options. We have a couple different models that may tailor better for, again, a high particular axis. Maybe it's a high bending you need, or maybe it's a high axial. We've got different flavors there. But now maybe you may end up with something that it does need to tolerate quite a bit of load, but you really need sensitivity or accuracy in one of those axes. We can specialize the calibration to kind of zoom in, if you will, on that area, provide specific data points, and give you more confidence, right? And you don't have to worry about linearity errors or anything in that, or even crosstalk, because we can likely calibrate and take that into account at that time. All right. Next section, back to instrumentation. Peter, why don't you run with this?
All right, excellent. Next slide, please. On your instrumentation, right, as I discussed before, that sample rate has to be fast enough to capture any of the peak values, transition values that you're looking for. Check that your filtering isn't limiting any sort of that data. So you've got three things to think about. You've got your load cell, the frequency that it can run at. You've got any sort of amplification that you might be using. Is there any filtering on the amplification? Even if not, now you've got your DAC system, your monitoring system, that might have some filtering on it. So all of those have to be congruent so that you can get the frequency of data that you're looking for, whether it's analog or digital. So sometimes analog displays have a little bit more filtering in them. So you want to make sure that that's going to be updating fast, updating fast enough for you to be able to look at the data that you're interested in across the entire system. Okay. You have analog to digital bandwidth, both for internal processing as well as pass-through considerations. So you might have a great DAC, you have a great load cell, everything's good, but if you put an amplifier in the middle of it that's only got, 300, 400 hertz, you might be tossing some of your data out before you ever even see it in the DAC system, right? What if I need event capture? Are there triggers? What if I want to shut it down in case something, I get one of those peak values or valleys? Well, we have that capability as well. If you need a special calibration, we can do E4 calibrations on your load cells. And then, as Brian mentioned, we have the 5200 series load cell that measures your moments both in X, Y, and Z. All right, next slide, please. Thank you. Consider using any sort of instrumentation triggers. What will that mean? Well, that allows you to place start and stop data capture criterion. If it's going to be running for weeks on end, maybe you don't want to capture the first 100,000 cycles. Maybe you do, but whatever. Or if something were to happen, you want to be able to stop the hydraulics, stop the controller, whatever it is, so that it doesn't continue. You want to have cycle count or event-specific type triggers just to minimize the data logging. Any sort of test anomaly, again, safety stop, deviations outside of expected parameters. So if you have a set trigger level where you think it should run and something happens outside of that, you can set it up to stop as well. Set point relays for any sort of analog device or limit switch triggers to control outside equipment. So for your assessment of your instrumentation, so physical limits of the load, your sensor, phase management could be necessary, characterization, your function of your load, perhaps some software compensation, sensor compensation. If you need an accelerometer, that's a consideration as well for accelerometer-based phase adjustment. Integrated accelerometers are an option. All right, and to the right there, it shows several of our instruments that can be applied to this type of testing. All right, next slide, please. All right, very good. On the use cases, next slide. For prosthetics, right? If any of you have done any work with FDA, I can, by my own experience, any sort of pacemaker type operation, everything has to be tested quite thoroughly. Well, so do prosthetics. And so the fatigue testing, they use one of our S load cells, in this case, a fatigue rated load cell, into our 9870, which then was put through a PLC into a laptop so that you could monitor the data.
All right, pretty basic fatigue test example here. This is the luxury edition of an F18 apparently, but no, very, very common application for interface load cells, full-scale fatigue testing. 1248 is highlighted here just as an example, again, to be able to integrate directly with the actuators that were used. Fatigue-rated flange model, good for 100 million full reverse cycles. 1000 series work well. And again, even if you have some unique situations, if sized properly, a 1200 series or 1100 series could work too. So, but these are very, very common applications, sometimes indoors, sometimes outdoors, where we can institute a few options to ensure extended load cell life.
Right. This one was also very interesting. They started out using a single axis load cell to determine the durability of their automobile seat. And so over time, they kept having failures of the load cell itself. They went to larger capacities. That still didn't solve the problem. And so what ended up happening was they went to a 6-axis load cell, installing into the machine, and then discovered that there were not only forces and moments that had not been identified, but they were able now to monitor those in their testing and then have that data as well. This was used with a 6-axis into that BX8 I spoke about earlier, and that has some of our latest, what we call BlueDAC software.
All right. Example of a basic component fatigue test setup. So using our 1000 series fatigue rated low profile, doing push-pull testing on a component. In this case, packaged with our INF USB. Nice thing about it is it comes with software. It comes with start-stop triggers, just like we talked about earlier. So it's real versatile software included with the instrument. Allows you to have pretty much a turnkey data AC testing solution ready to go. So again, doing fatigue testing, need push-pull, 1000 series, always the best bet.
All right. This one, something I'm very grateful as a bicyclist, they do fatigue testing on your handlebars. And so again, this also is an SSMF, goes into what we call the SI-USB4. So that takes the millivolt per volt output of the SSMF, digitizes it. Again, it has its own software as well. And then that's data log through the computer.
All right, it's like we're winding down here. Appreciate everybody being on this morning. So we'll go through some FAQs here. So let's see, what do we have in store for today? All right, so can you use a load cell not fatigue rated for fatigue testing? Peter, what would be your answer on that?
The answer is yes, but you need to make sure that your capacities, that SN curve that we discussed earlier, are well within the requirements of what you need for the longevity of the test.
Right. What is the highest cycle count recommended for a single load cell?
Well, our fatigue rated are 100 million cycles.
Yes, and I would say,
yep.
Yeah, and again, in our 50 plus 60 years of selling load cells, we haven't had fatigue rated 1000 series come back with a fatigue failure. So I think the answer might be unknown at this point for high cycle count. Next one.
How can load cells fail in fatigue?
Well, the most common way we see them fail is due to unknown off-axis loading. So do everything you can to isolate best you can. If you've got some concerns going up a little bit in capacity, usually not a bad option. Again, as long as you can handle the inertia, the mass, the dimension, just want to make sure that you can tolerate. You just really don't want to get 9 months into a 10-month test and have a failure. Now, some things could go wrong with a bridge. It's rare. If you are doing fatigue testing, we didn't mention this thus far, but we typically would recommend dual bridge. It's very common. Some of our sensors, some of our customers even do triple bridge for their fatigue test setups. So why a second bridge? Well, it's redundancy, right? You can have the second bridge just running in your data ACK as well. In case something does happen, maybe with the sensor bridge, or heck, maybe something happens with the cable, right? If it's a setup. You won't lose all that test data. So second bridge, relatively cheap insurance. And again, maybe you can use it to control or something different, but just from a redundancy standpoint, for a high investment fatigue test, not a bad option. What is the recommendation for mounting load cells for fatigue testing, Peter?
We covered that previously. We have an installation guide for the 1100, 1200 series, the 1000 series. And so to follow those, as you put down the jam nuts to make sure that it's mounted correctly, and then that it has only the axial loads, and then you can account for or negate any moment loads that might be affecting your test.
All right, what is a set point? Well, set point could be either software or it could be relay driven. Many of our panel meters will have set point options where you can set a particular force value to where it'll then trigger a relay on the back. And that relay can then go and maybe signal an alarm. It can signal a light. It can maybe shut off a hydraulic actuator, shut down the test. So you don't need full-blown data ACK necessarily to be able to set up a fatigue test stand. So set points are good to understand, and we certainly can help with different options depending on what you're looking to test with.
Yeah.
How often do you need to calibrate the sensors used for fatigue testing? Well, I'll go ahead and answer this one.
All right, sir.
Sensor calibration in general, it's kind of up to the customers. We recommend annually to start. After that, if you've got good confidence, fine. Now, fatigue testing is a little bit different. If you're going to be performing fatigue testing, best practice would be to have sensors calibrated before a big test, run the test, and then have them calibrated again. That'll bookend your data, give you high confidence that what you ran and the data you collected was just as good at the end as it was when it started. So that's what we recommend there.
And that there was no damage to the sensor.
Correct.
Yeah.
So what type of indicators are used for fatigue analysis, Peter?
Well, you're going to want something that, as we discussed, a high bandwidth, high sample rate, the ability to, if it is filtered, that it's going to be higher than what you're looking for out of the load cell in terms of the operation frequency. And so it can be analog, but DAX might be a better solution certainly for fatigue testing.
All right. What is natural frequency?
If you think about natural frequency of these load cells, we showed you an example earlier of the 1200 series. Different capacities had different natural frequencies, but if you electrically, you can look at it as a low pass filter. So everything below that frequency can be registered by the load cell.
Going back to the electrical reference, yes, or mechanically, it's a spring that starts to get out of control, right? If you start oscillating too fast. So, but as we kind of suggested, good practice is going to have us pretty far away from the natural frequency.
Yeah.
But it's not to say that you can't start to push that. But in our experience, by the time you factor in the actual loads, right, which changes the system level natural frequency, things are typically operating around 60 hertz for most force testing. That's still pretty quick. Obviously, if you're going faster than that, we can get with you on that. But natural frequency is just good to understand the mechanical aspect and understand how it impacts. Again, think of a load cell as a spring, very stiff one, but still a spring. Do you need to consider overloading? How would you answer that?
Absolutely.
Yeah, so not only from the extraneous loads, like we've really beat with a stick here, but also overload your test article. What happens when that thing fails? Are you okay with writing off the rest of your test stand, or do you want to take some precautions to ensure that everything else outside of your DUT is in good working order after you go to failure, right?
Yeah.
How does speed factor into fatigue testing analysis?
Well, again, we discussed that it has to be lower than the natural frequency. You have to have any filtering in your amplifier, your DAC. Everything has to be congruent so that there's no filtering lower than the operational speed. In fact, you want the DAC at least 10 times faster than the operational speed of what you're running the load cell at. So it does factor into it. Again, we talked about the normalized operating speed of some of these fatigue tests tends to be right around 60 hertz.
Good. All right, last one. What about friction or heating effect? So this is an interesting question. I think it's from a sensor standpoint, there is no internal friction or heating that's occurring, regardless of cycle speed. So load cell, it's not an issue. Now, if you have friction or heating elements from an environmental standpoint in your test setup, your test environment, then of course, yes, the load cell, if it thermally changes temperature, it's going to impact the zero balance, potentially the span. We can certainly address that. We have specifications on it. We've talked about it in some other webinars. We got a lot of content out there. But again, just because you're doing high cycle testing doesn't impact how the load cell performs, and there's no internal heating or friction or any concerns of that nature. So
We've got a
all
question
right.
from Jay. He wants to know what you recommend for calibration intervals if you have a test that spans multiple specimens over a few years. His reference 3 million cycles per specimen at a low frequency, 3 to 5 hertz, with multiple inspections during test.
Okay. If I heard the details correctly, if as long as the test is, if you complete a test within a year, I would recommend just until you start having good data, to have the load cell calibrated annually, right? Now, if you do it and the load cell still looks good, no change in performance, then maybe you can extend that interval out. We have some standards that we use for calibration that we don't have calibrated every year or every 2 years even, because we have 40 years of history. So again, there was a lot in there. I'll take a look at it if it's posted, and we'll get back to you if I have any more specifics on that. But it's going to be kind of your call. If you're using a fatigue-rated load cell, you have super high confidence it's not seeing any extraneous loads, then yes, it should be good for many, many millions of cycles. But calibration intervals is more a confidence factor and ability to maybe document that there's been no change. But if you can do a test, get it done within a year, that's a long test. I would still recommend doing a pre and post cal. If you've got a couple of those that look good, high confidence, then you can maybe extend that interval. So if I understood the question right.
We've got another one here. When tuning PID loop for a test, sometimes the loop goes unstable. Is there anything other than going over the safe overload to be worried about as far as load cell damage, such as vibration, etc.?
Okay. Yeah, so that's a good question. So it sounds like it's kind of a runaway system, high dynamic. First, I would be concerned, do you really have confidence in what the load cell was seeing, right? Whether it be from a cycle count or from a force. We could be missing some of that from a data standpoint, like we talked about. So the load cell, your first concern is the right one. Did it see high overload? And again, that would be an inertial overload, right? Potentially. That would be the first concern. I would say if you're done with the testing, or you shut off an out of control scenario, you shut down the test. If the zero balance is still pretty good, if it's about where it started and didn't see a big shift there, you're probably fine mechanically. Outside of that, the only concern, of course, is that it's oscillating so quickly that you're not getting good data. You've either got some phase lag or, again, if you're going too fast, then it's starting to get underdamped, and that's going to introduce some error there. But zero balance is a good check, always to make sure that you haven't done any, if you've worked into that plastic damage zone for the load cell. And just real quick, while we're on it, even if you do see a little bit of zero shift, oftentimes you may still have pretty good linear performance. Our load cells, we calibrate them out to 100% of capacity. Reality, you've probably got about a 10% there for our LPs over it, but they should still stay pretty linear. So if the zero balance is good, you're probably good. If you saw a zero shift, you can always send it in for recalibration, and you're likely still got a good sensor. You may have used up some of the overage over capacity. So as long as it hasn't moved up, 10, 15, 20%, shouldn't be an issue.
We've got one more. Can you elaborate more on the dead side, live side, the dead end, live end part of the conversation we just had? Was there a recommendation on what side to attach the actuator to? And lastly, do
Yes.
you mean the strain relief for the cable plugged into the load cell?
Okay. Yeah. So good questions there. We probably should have had a cutaway model in here to help show where the gauges are. But the best way to think about is which end of the load cell has the least amount of mass or is closest to where the really you want your test article probably on that side. So on the S cell, if you remember, we had the label in the middle. Gauges are right behind that. Cable comes out of the right. That would be the dead end. On a low profile, the dead end is going to be essentially not the hub, right? So you've got the outer ring attached to the base. On a low profile, we've got the center top loaded hub. That would be the live end. We typically recommend you have the load cell mounted on your actuator on the dead end. That just puts your test article closer to the live end and less mass and less things impacting your measurement of what your test article is seeing. Was there another part to that question? Something about a cable?
You had mentioned the strain relief for the cable plugged in. Is that the cable plugged into the load cell?
Yes. So you'll have a cable. You'll either have a mating cable that plugs into a connector on the load cell, or you'll have an integral cable coming out of the load cell. And it's just important to pay attention to where you strain relief that. Strain relief meaning you've allowed for an adequate service loop so that if you are translating through a certain amount of motion that you've got a service loop to accommodate that, but you want to have that cable secured if you can. And again, you want to have it somewhere on the dead end if it's a horizontal test, or somewhere on the dead end if it's a vertical, somewhere down below. You don't want to have that cable zip tied up to maybe something up on the other side of your test article, right? Because now you've introduced a parasitic load path outside of that bridge where now you've got not just the thing attached to the live end of the load cell, but now you've got this cable that's also influencing around the bridge. Hopefully that helped.
That was
All
very
right, Jamie.
helpful. No more questions, but let me just give you first, thank you, Brian and Peter, for a very informative conversation around fatigue testing. A lot of material. It did go fast. We tried to cover that in an hour. So you will find this link on our YouTube channel. I'll also be sending you an email where you can easily access that. There was a question to access the presentation itself. I'll also provide a link where you can download that just based on the size of the presentation. It makes most sense to do it that way. So first of all, just wanted to say thank you again. Why interface? Well, the fact of the matter is we're a trusted partner. We've been building sensor solutions it's running into almost 60 years now. We have engineers that design all of our products in-house, and they build, test, and distribute our products around the world. So we've been doing this for a long time. We've seen a lot of application uses. We've seen things that have worked really well. We've also advised people on ways to avoid failure. So I think this conversation has been very insightful around that. If you have questions, as noted multiple times, please reach out to us, Brian and Peter, as well as a team of representatives and distributors around the world are here to help. And we do design our load cells for precision. We have high accuracy. They're built to last. We customize our products if you have special needs that require a use case that is not perfectly defined by a standard product. Get with us. We're one of the very few that engineer our products to order, as well as offer custom, especially on OEM products where you're looking to do something on an integrated solution. Lastly, if you have not, make sure you download our load cell field guide. We put a lot of this kind of technical content in one resource. It's available online, or contact us. Happy to send you the link, but it's free. It's very technical, got a lot of resource to it, a lot of the definitions of the terms that were used in this presentation for anyone coming new into test and measurement. So last but not least, let's connect. We'll keep you up to date on our next webinar. Rumor is we're going to talk about torque. So stay tuned, and we hope to see you either at a Force Leaders event or online soon. Thank you, everyone.